Okay, so here we're going to be reviewing the heart. Again, some things I'm just going to go over briefly, which you will hopefully look into more. It's just a little bit of that foundation kind of information that you might need, but I'll go over some of the more complex things. But yeah, so just to start off, we get into functional synctia. What this is essentially saying, or what it is it's how the cardiovascular system works. Like, they have to be in sync, so that's that part of the word synctia. So they have to be in sync. There is atrial synctium, or syncytium, however you want to say it. And it just has to do with how the atriums, both left and right, sync up through the conduction of the electrical signal from the SA node. And then you have ventricular synctium, which has to do with the AV node. And we'll get into that as we go further on. But just know that they just are supposed to sync up and contract together and pass along the signal. So the SA node, I've reviewed with some of you guys already, is really the pacemaker. So it kind of starts the heartbeat and the rhythm of the heartbeat, right? So heart pumps blood continuously all the time. It has a rhythm. And here, precise electrical events initiated by the conduction system. This is the conduction system, right? So you have your SA node, your AV node, your right and left bundles, and your Purkinje fibers. That is your conduction system. The conduction system, as we'll learn a little further on, is kind of made up by nodal cells, or at least the SA node and the AV nodes are made up by nodal cells, and they act a little differently from our cardiac muscle cells. And we'll get into that as well. But another keyword to know, action potential, essentially just like an electrical signal that's being fired throughout. And there's certain things that each cell needs to do, or that needs to be achieved before a signal can be sent out. So we shall continue. And another thing is, this is important as well. Ensures atria contracts prior to ventricles. When we talk about the SA node, we're talking about the contraction of both right and left atriums before the ventricles contract, okay? So here, these chambers, like if the signal were to progress from here, it is not just progressing on the right atrium, but it's also going behind into the left atrium. All right, so that's a good basis to start off. Again, initiates heartbeat, is the pacemaker. So the SA node is the pacemaker. And we continue. Ventricular node. Yeah, so then you have your AV valve as well. So right here, if your signal starts, and it'll cascade down until it reaches the AV valve, but the atrium will contract, both will contract before the ventricles. All right, let's go on. Again, SA node is your pacemaker cell. We also have two cardiac sensors that are within the medulla oblongata. You have a parasympathetic and your sympathetic pathways. Parasympathetic is your rest and digest, right? And then your sympathetic is your fight or flight. Okay, not just two fights. Got a lot of fight. And they can either be cardiocellulatory or cardioinhibitory, meaning that they are affecting the heart, right? Because cardio, acceleratory meaning can speed up, or inhibitory slowdown. Sympathetic is that cardiooscillatory. I believe this is T1 to T5, which is your thoracic vertebrae. I'll write that here. So it comes from your thoracic vertebrae. And this comes from, I believe, your vagus nerve. If I'm not mistaken, I just want to double check. Yes, your vagus nerve, cranial nerve 10. So this would be your vagus nerve. All right, so now we've established that parasympathetic, rest and digest, vagus nerve is our cardio inhibitory, right? Inhibiting the heart rate to increase because we are resting. So parasympathetic is cardio inhibitory. In the sympathetic, we have cardio oscillatory because it's our fight or flight. Acceleratory. Okay, I'm definitely saying that wrong. Acceleratory. So here we're doing an overview of the parasympathetic. Rest and digest, cardio inhibitory, it is going to decrease heart rate. That is the main takeaway. The right vagus nerve innervates the SA node, whereas the left vagus nerve innervates the AV node. So this is the pacemaker. And then this is the one that will contract the ventricles. And then sympathetic innervation is a cardiooscillatory with the neurons from the T1 to T5 segments of the spinal cord. Extend to these four particular spots: the SA node, AV node, myocardium, and coronary arteries. I wouldn't say that this is something you particularly need to know. Mostly just the sympathetic and the parasympathetic innervation, and the cardiooscillatory and the cardioinhibitory. Where they innervate might also be slightly important, but main thing to know would be sympathetic innervation will accelerate your heart rate, and inhibitory will decrease heart rate. This shows you a better picture of the centers. So this is the cardiooscillatory, right? So this would be T5, which it goes out to these 5 vertebrae, and then it will innervate in those 4 areas that it said it would: coronary arteries, etc. And then this being the vagus nerve, right and left. The right innervates at the SA node, and the left innervates at the AV node. Right. So in the innervation of the heart, there are also some chemoreceptors and baroreceptors that help us detect what changes need to happen. Chemoreceptors are looking at the ions in our blood. So chemo is the ions, where baroreceptors have to do with the pressure, but particularly the pressure in the chambers of the heart. So we have atrial reflex, and this protects the heart from overfilling. There are baroreceptors in the atrial walls of the heart, and essentially this protects the atrial walls from overstretching, and losing that elasticity and strength to contract. So it is trying to protect that ability. So when there is an increased venous return, nerve signals increase the cardiooscillatory center. So if we can pump more blood out of the atrium, we can decrease the pressure because we will not retain as much blood there. So heart rate is increased so that we can decrease atrial stretch. right? So this is a way that these baroreceptors help us, at least in this way, would be, since it is increased, it would be sympathetic. Sympathetic, which is cardioacceleratory. So then there are not two systems, but there is the conduction system, which is kind of what we're talking about. So it is the SA node, the AV node, the right and left bundles, and the Purkinje fibers, right? So that's like the electrical activity that's initiated at the SA node, and it propagates through this conduction system, right? Going through your right and left bundles, etc. And then you have your cardiac muscle cells, where they will spread the action potential across the sarcolemma of the muscle cells, right? So sarcolemma is like this covering that they have across all the muscle cells, and it helps propagate that action potential. So again, first in atria, then in ventricles, there's the two functional cinctia, right? Sorry about that. So then we have the stimulation of the heart. We have that conduction system. So initiation begins at the SA node with these nodal cells, and it will spread across that conduction system, right? So our SA node, that signal will propagate. It will reach our AV node. From the AV node, we will then move on to the right and left bundles, which will then reach the Purkinje fibers. And what is interesting is that the heart will pump from the Purkinje fibers upwards. So it's essentially sending the signal from the apex of the heart upwards towards the atrium. And it does that because that is in the direction it needs to contract to send blood up each valve, whether that be the aortic valve or the pulmonary semilunar valve. And then, once the action potential has been initiated by the conduction system, the sarcolemma will propagate it, right? So the action potential will go across these, and it will propagate that, and the muscle contraction will occur, which are these filaments that there are thick filaments and thin filaments, and they will contract. So this is relaxed, and this is contracted, or contraction. So here you'll say, causes cardiac muscle cells to reach threshold, and then they will do the contraction. So here are our nodal cells. I'll erase this because I'll redraw it. So here our nodal cells have a resting membrane potential of 60. So we'll have to kind of get familiar with the action potential and what they need to reach their action potential, how they fire, etc. So they generate the action potentials, and they're the pacemaker cells that initiate the heartbeat. So these are the cells of our SA node, right? Because that is what starts the heartbeat. And the most important thing here would be our sodium-potassium pumps. And they have sodium-potassium leak channels that help maintain this 60 MV or 60 millivolts. Main things to note is there is a greater concentration of sodium outside the cell. There's a greater concentration of potassium inside the cell. We also have calcium ion pumps, and it creates a calcium gradient with more calcium outside the cell, right? So these three are really important to note here at the nodal cells. We have slow voltage-gated sodium channels, fast voltage-gated calcium channels, and regular voltage-gated potassium channels. So I will show you what that looks like. There is this image here, which I will erase this. And this kind of shows us what an action potential looks like. So you have a resting membrane at 1, right? So this is your resting membrane. This is your signal or your depolarization. And this, the whole number 3 on our way down, is our repolarization. And these ions flow in and out during each of these steps. And here at resting membrane potential, we start at negative 60 millivolts. At resting membrane, we know that potassium has a higher concentration in cell, or in the cell. Sodium has a higher concentration out of the cell. And calcium has a higher concentration out of the cell. In order for us to get to this threshold here, to fire our action potential, right? So this is what we want to do. There needs to be a change in ion concentration from here to here. So what occurs in this point is that sodium will rush into cell. Or not rush, because sodium at this voltage gated ion channel is slow. So sodium slowly flows into cell. And sodium is positively charged, so we will get closer to a positive charge. So we're getting closer to 0. So as we slowly get closer to 0, we will hit threshold. And once we hit the threshold, there will be a fast flow of calcium rushing into the cell. And that pushes us a little bit more positive, so further towards a positive direction. This is called depolarization. This depolarization is that action potential we want to reach. So we will reach here, in which we fire that electrical signal. Once we get here, we have achieved what we needed to do, and we need to get back to resting membrane potential in order to fire once more. In order to do this, we have to become negative. So we have to let go from inside the cell of a positive ion. That positive ion will be potassium. So potassium will flow out of the cell. So the potassium will flow out of the cell, and we will reach resting membrane potential. With the leak channels, it will finally balance out, and then you will again have potassium in the cell, or potassium concentrated in the cell, sodium out of cell, and calcium out of the cell. And just to be sure, this is just here in our nodal cells. They have different charges that we will see in the cardiac muscle cells. It's different from how our neurons in our brains fire, or our peripheral nervous system. This is just for the stimulation of the heart here. So then you will see in cardiac muscle cells, some of these switch. So some become fast where they were slow, and some become slow where they were fast. So we will get to that when we do. But here it starts to explain each step. So 1, the resting membrane potential at the reaching threshold step. We have sodium flowing into the nodal cell. From what we remember previously, it said slow voltage gated sodium channels in nodal cells. Right? It doesn't say it here, but if you get a question asking sodium flows out of a cell blank as sodium flows into a cell blank as calcium flows into the cell, it would be slow for sodium, fast for calcium. And it might change. Make sure you check that you are looking at nodal cells. or the conduction system of the heart, stimulation of the heart. Right, so open calcium channels will lead to depolarization. Potassium opens will repolarize. And writing it out yourselves will help you understand it. Make sure you know what's going in and out, the concentrations. Here's the depolarization. Calcium, fast voltage gated calcium channels triggered to open. Entry of calcium into the cell. Memory potential from -40 to just above 0. And then we will repolarize. Opening of voltage gated potassium channels with calcium flowing out. So all the other ones were flowing in. Entry of calcium into cell. And this one was flow of sodium into the nodal cells as well. So typically, our heart rate, our inherent rhythm is faster than 100 beats per minute. That's not good. Like, go for a run or something. But we have something called vagal tone. Vagal tone is the slowing of our heart rate. So it's parasympathetic stimulation, because we know parasympathetic is cardioinhibitory. And that's that vagus nerve, right? The right and left vagus nerves innervate the right to the SA node, the left to the AV node. And again, the bolded terms, always look at them for a bit, see if you might need them. So here we see nodal cells do not require stimulation, unlike neurons, correct? So neurons need there to be sensation, and like a certain amount of a signal needs to reach your skin for it to then pass it on to your spinal cord, to travel to your brain, to integrate the information. This does not need that stimulation. There will be sodium slowly flowing constantly into the nodal cells, reaching that threshold, allowing for calcium to flow in, reaching the action potential, and then you're repolarized, and you'll do the same thing over and over again. And then here, these images are good to look at as well. Going back to our muscle cells quickly, they have gap junctions as well. I don't know if you may have learned gap junctions in Bio 40 or Anatomy 1. But gap junctions allow cells to communicate basically directly, not needing things like hormones to communicate or anything like that. So the electrical signals will also pass through, or other things can pass through the cells fairly easily. So down here in this image, if we read first, an action potential is generated at the SA node, and it spreads via gap junctions between cardiac muscle cells throughout the atria to the atrioventricular node. Right. So here, here we have our SA node. Our nodal cells do their thing, right? They have sodium flow in, reach threshold, calcium flows in. You finally have this signal, right? Boom, we got lightning. This signal will then propagate throughout the atrium. And it'll go throughout the atrium, and it will also reach the AV node. Right? And again, here, do not forget that it does go into the left atrium as well. And we will reach all throughout the atrium. The atrium will contract first, and the nodes are only at this exact point. Everything outside of this is cardiac muscle cells, right? So all of everything that it is sending the signal to is the cardiac muscle cells. It is not sending it into the blood. So then, our heart somehow knows that it wants to delay the action potential to the AV node before it passes to the AV bundles within the interventricular septum, right? So this is the interventricular septum. So it wants to wait for the whole atrium to contract before it passes along that signal, because we can't have both our atrium and our ventricles contracting at the same time, because our heart will stop. We're trying to push blood this way, we're trying to push blood that way, everyone's trying to push blood one way, and it just won't work, right? So the AV node, so politely, just waits, and the signals, again, propagating from the SA node, will go across the whole atrium, both right and left, and then the AV bundle conducts the action potential along the left and right bundle branches to the Purkinje fibers. So erase this. Now that the atrium has contracted, right, there's no more signal here. That signal has reached the AV node, and the AV node is now going to propagate that signal, the interventricular bundles, all right? And then we split off into right and left. And then here, the action potential, the same as in the atrium, was spread via gap junctions between cardiac muscle cells throughout the ventricles. And again, here, stimulation begins at the heart apex for the ventricles. That means it starts here. And again, that reasoning for that is that you want to push blood in this direction. So that signal is moving in the direction you want to start contraction. So you start squeezing here so that the blood moves up and that pressure increases. Let's just say that the pulmonary semilunar valve is here. And in this instance, we're going to try and push open this aortic semilunar valve so that we can have the pressure change upwards. Again, papillary muscles stimulated to contract immediately. Muscles anchor chordae tendinate to AV cusp. And we'll also get into how this is that QRS segment or QRS complex. But, every wave is associated to a specific depolarization, repolarization. Okay, so then action potential, I guess this is like a brief overview again. Action potential is distributed throughout the atrium, and it's sent to the AV node. It's spread through gap junctions of the atrium cardiac muscle cells, and the gap junctions, because it's so easy to communicate between all the cells, it's like almost instantaneous for the muscle cells, right? So then the atria contract at the same time, both right and left, and the action potential is delayed at the AV node. The AV nodal cells with smaller fiber diameter and fewer gap junctions. So it slows the conduction rate, and so there's a fibrous skeleton. You won't have to really know, but it's what allows the signal to only flow through the AV bundle instead of also just touching the other muscle cells into the ventricles. And then that delay at the AV node allows the atria to finish contracting, and it forces the blood into ventricles before the ventricles can contract, right? If we were all just contracting at the same time, we'd have a whole lot of, like, a really messy heart. Action potential to conduction system. Then we move through the AV node, into the bundle, into the fibers. And then it'll spread throughout the ventricles via the gap junctions through your cardiac muscle cells. And again, 120 to 200 milliseconds after the SA node fires, super fast, right? We can't comprehend how fast that is. That means that both atrium contracted, and then that signal was sent through the AV nodes, or through the AV node, right? Through the AV node up to the Purkinje fibers, all within 120 milliseconds to 200 milliseconds. So yeah, like, it's a very brief pause at the AV node, but still a pause. It's a very important pause. I'm not too sure if you will have any questions on things like this on your exam. So again, look over it if you want to be well prepared. We're going to get into the cardiac muscle cells. So at the cardiac muscle cells, this is essentially what happens after a conduction system, right? So the conduction system, again, is the SA node, AV node, the interventricular right and left bundles, and then our Purkinje fibers as well, right? So these are providing the signal. They do not spread the signal. The signal is then spread through the gap junctions of our muscle cells. So we have the sarcomeres, which are cylindrical things that make up our muscle cells. We'll get a little further along into it. I think they bring it up a bit later. So there are essentially two systems to propagate the signal, and we're going into the cardiac muscle part. So here we have a resting membrane potential of negative 90, right? So it's different to our nodal cells, which was negative 60 millivolts. Here we also have our gated channels, but like I mentioned, we have different speeds. So now our calcium, instead of being fast, is slow, and our sodium, instead of being slow, is now fast, right? So what does this mean? Slower depolarization, faster reaching of threshold. So we can essentially fire our muscles a little faster, right? We'll get to that point a little faster. But the only thing is, it does need a signal. It needs that electrical signal to get there. So we still have our sodium-potassium pumps, Na leak channels and potassium leak channels to balance the cells. Again, lower resting membrane potential, and still the same greater concentration of potassium inside the cell. And we have calcium pumps to form a gradient with calcium that is outside the cell. So the pumps and channels within the sarcolemma, again, fast voltage. So nodal cells or any of the conduction system in the heart has slow, whereas the muscular cardiac system has fast sodium channels. And they participate in depolarization at membrane. The potassium voltage gated channels participate in repolarization. And we will get into calcium in a bit. So here we can see that instead of essentially reaching threshold, we have a straight shot up. And this straight shot is just depolarization. So this would be our fast sodium channels now. It's extremely different from our nodal cells that needed to reach threshold with sodium, flow in calcium, and then flow out potassium. So here we'll read depolarization, the action potential transmitted through conduction system, triggers opening of fast voltage gated sodium channels in sarcolemma. The entrance of sodium into cardiac muscle cells, resting membrane potential from negative 90 to positive 30. So these essentially are the depolarization. So this is the first step in cardiac muscle cell, right? Just straight to polarization. There's no need to reach threshold. And these voltage-gated sodium channels will close to an inactivated state, right? So this is important to note. So that is this. then to our plateau. So this is the occurrence of electrical events, right? So it opens voltage-gated potassium channels. So we went from in nodal cells needing sodium, calcium, potassium, to now in cardiac muscle cells, sodium to potassium, and we'll leave the muscle cell. And as we decrease in our plateau, and then we'll plateau, which means to flatten out, we'll see that we repolarize at a certain point, though not as steep as our depolarization. So this slow and long repolarization is in relation to this slow voltage-gated calcium channels. So here we'll read that the potassium, bringing us back to a little negative, will open the slow voltage-gated calcium channels in sarcolemma, and that allows calcium to enter cells. And then there is no electrical change in the sarcolemma, and it remains in depolarized state, right? So we're like in this weird state, and then we will repolarize. But it remains for a long time in a depolarized state. The repolarization is when voltage-gated calcium channels are closed, and then potassium remains open. So in our nodal cells, if we remember, in order to repolarize, potassium needed to remain open. So calcium essentially here is prolonging the depolarization. And that leads to that plateau, which is why it's so drawn out, because both potassium and calcium are interacting, right? So calcium is flowing in and potassium is flowing out, right? So potassium is flowing out, which would depolarize. Or not depolarize, sorry, repolarize. Right, so we'd be going back to our negative 90 millivolts. But because the calcium channel is open and calcium enters, which in the nodal cells was what got us to depolarize, it will prolong repolarization, right? So we can't go back down because this calcium is flowing into the cell. And once then those close, then we will get that whole repolarization effect. One thing to note here are cross bridges. I guess they haven't shown you what a cross bridge is yet. Is there a picture of one? No. Sweet. How about further up? Okay. So I'll just use one of these. So essentially, this is a myosin, I believe. Let me just double check. I believe that is a myosin. Yes, correct. So this is the thick filament of a sarcomere, right? So myosin essentially is a line like this, and it has these cross bridges. So these things are called cross bridges, right? And this is essentially what it looks like. And you have these, so these would be the thick filaments. We just call it thick fill. And then we have our thin filaments, which will look like this. Right, so this would be thin fill. And this is at a relaxed state. Let's put relaxed. But when they are contracted, I'm just going to erase it. Or I'll erase, oh no, I'll erase thin fill. We're losing him. the thin filament will look like this. So it will be a lot closer to these, right? Before it was up here, let's say like that, not really overlapping with our cross bridges, but then our cross bridges and our thin filament will overlap. So we'll return to that point we were at, which was repolarization. Oh, so the mechanical events cross-bridging cycling. So the entry of calcium into the sarcoplasm, right, which is the fluid or space in the sarcolemma, will initiate the mechanical events of muscle contraction. And the calcium ions binding to troponin, which is part of those myosin, right? It's like I don't know why they haven't really shown you much of it. You might not really need to know too much about it as I'm going through the chapter, though. I'm just going to give you information. If you want to hold on to it, you can, depending on also what they told you at lecture. Take that into consideration when you are studying and when you're listening to me. Like, if whatever I'm saying is not needed for your exam, don't even listen to it. Focus on what you might need for the exam. So these calcium ions bind to troponin, and they will begin that cross-bridge cycling. Calcium levels will decrease, release from troponin, the cross-bridge decrease between the thin and thick filaments, and they will return to a relaxed state, right? So they contract and then they relax. Skeletal and cardiac excitation are similar in the sense that they both have a refractory period, and it's after depolarization when a muscle cannot be stimulated, right? So here it said that, not here, but in the first part, in our depolarization, it will say that our voltage-gated sodium channels close to an inactivated state. This means they cannot fire, right? So refractory period, important. Know it for your exam. It means that the cell cannot fire, no matter what stimulation it gets, right? Can't be re-stimulated. They both have depolarization and repolarization. They both have contraction and relaxation, and both have a lag time between action potential and contraction. And then they differ in the way that the refractory period is longer in cardiac cells, but it also has a longer duration of action potential because of those calcium channels that are open and calcium is coming into the cell while the potassium channels are open and potassium is leaving the cell. So you have this positive ion leaving while the positive ion is coming in. There's really no change, so you plateau, right? Just a little recall to that whole action potential for the cardiac muscle cells. It takes longer, 250 milliseconds compared to 1 to 2 milliseconds. Is that needs resting memory potential. Sorry, I'm just a little confused. I don't know which ones it's talking about. Make sustained. Yeah, so you can't keep a sustained contraction in your cardiac cells, right? Like if your cardiac cells were to just not be able to contract, you die, right? So it allows the heart to always contract and relax and continue pumping. So here, muscle relaxation. So this is muscle. This is what it looks like in our nodal cells, our skeletal muscle. Sorry. What is this saying? Okay. So our skeletal muscle being like our biceps or whatnot, this is what that action potential looks like. And this would be the lag time between the two. And then this would be the whole length of muscle contraction. So it takes about 250 milliseconds for you to go from contraction and relaxation from, like, let's say something like your bicep, compared to the heart, where you need that, reach that membrane potential, and you depolarize, and it will stay open for a long period of time, and muscle contraction will start while it is in that plateau phase. So the main takeaways here is that this action potential will go back to resting a lot quicker in skeletal muscle, allowing for a lot of contractions. And here the prolonged refractory period before it can fire again makes it so that sustained contraction is impossible. The charts don't necessarily look like what it's saying, but it is that, right? So your heart just can't sustain contracting for a long period of time. So moving on from that, we'll go into the ECG recordings, right? So again, I said each part or each thing that occurs in the heart shows up here in this chart. Again, you don't need to know too much of this. Also use your judgment based off what was said in the lecture. We have our P wave, QRS complex, our T wave, right? So these are the waves that we see. So P wave is this thing, this one right here. All right, so here at the P wave, it reflects electrical changes of atrial depolarization, right? So this would be when the atrium is contracting. And it originates in the SA node. So we now know this is associated to atrium contraction. The QRS complex is the electrical changes associated to ventricular depolarization or ventricle contraction. So the atria are repolarizing almost at the same time that the ventricles are depolarizing. So they are masked by the ventricular depolarization just because they're larger. And then we'll go into our T wave, which is associated with ventricular repolarization, right? We have repolarization here, which is ventricular relaxation. So this was, right, so QRS was all associated to ventricular contraction or depolarization. And this was repolarization. And then this was atrial contraction or depolarization. And somewhere here would have been atrial repolarization or relaxation. And then we go to our PQ segment. So that is not that, but this right here. And here it says is associated with the atrial plateau at the sarcolemma. Right? So at our cardiac muscle cells, that is the plateau. So as the prolonged action potential caused by the CA2 flow. And that's the cardiac muscle cells within the atria are contracting, right? And then our ST is the ventricular plateau. So again, going back to it, the cardiac muscle cells have that plateau, whereas the nodal cells do not have that plateau. The ST segment is the ventricular plateau. So the cardiac muscle cells in the ventricle are contracting. And the waves associated with depolarization and repolarization. Right, so this was depolarization. The QRS complex was depolarization for ventricles, and the T wave was repolarization for ventricles, whereas P was depolarization for atrium, right? So the atrium depolarization. So the flat lines have no electrical change, right? So those flat lines here in purple would be these lengths. So the heart is resting between beats, so we don't have that continuous ability to just contract, right? So we just are going to rest. So the signal is fired, and the cells, the muscle cells will fire and contract one by one. Essentially one by one. It's more of a cascade, almost simultaneously though, right? It's just, for us, it just seems like it's too fast. So it's just all at once, but it's very much just flowing through towards the AV node. And then the ST segment is the ventricular plateau, right? So heart at rest, and the same for the PQ segment, so it's just heart at rest. The interval is the time it takes for the conduction system to spread the action potential through the atrium. So the PR interval, which would be this one, would be the time, right? So time interval. So this is the time it takes for the atrium to contract. And the QT interval, it would be for the whole time that the ventricle contracts, right? So we start at Q, and we end at T. So then here we relax. Again, no systole and diastole. That will be important for your exam. Alternating contraction, relaxation of atrium ventricle. Again, know this, the pressure in the heart. Ventricular contraction. Right, so if you're increasing contraction, you're squeezing something, you're increasing the pressure. Know how the AV valves are pushed open or kept closed, depending. Again, this is like information that you'll have to study on your own. It's just, get familiar with what is opening and what is causing pressure. So contraction increases pressure, and it prevents backflow, right? So you're keeping the AV valves pushed and kept closed, whereas relaxation will close the semilunar valves, but the AV valves will open. So be able to know this as well. again, know that blood returns to the right and left atriums. Right gets deoxygenated, left gets oxygenated. The ventricles will fill passively. The AV valves open at the beginning of the cycle. The atrial pressure at the beginning is greater than ventricular pressure, and the semilunar valves are closed. And then, so the pressure in the ventricles are less than the arterial trunk pressure. And this is a chart you would like to really get to know. There's atrial systole, so at the contraction point from the atria, right? So systole being contraction. And then you have early ventricular systole, so early ventricular contraction. So the ventricles start to contract, and the AV valves are closed because the pressure is increased here in the ventricle. All right, so this is also important to know, so make note of it. So the pressure, like that pressure is higher here, but the atria is relaxing. So in early ventricular systole, we have both valves closed, right? In late ventricular systole, the atria is still relaxed, the vesicles are contracting, right? So contracting here, and we're still contracting here. And ventricular pressure is now greater than arterial trunk pressure and atrial pressure. So the arterial trunk being the pulmonary semilunar valve. And then the AV valve will close, and the semilunar valve is open during late ventricular systole, so during late ventricular contraction. And then as we go into early ventricular diastole, so relaxation of the ventricle, there will be some blood left over, and that is called your end systolic volume. That is something you'll have to know as well. But now the atrium is filling with blood, but the atria is still relaxed. So we're not constantly contracting, we're not constantly firing the cardiac muscle cells. And then the ventricular pressure is still greater than the atrial pressure, right? So the atrium hasn't opened the AV valves to get into the ventricle yet, but the semilunar valve is closed because the pressure is not greater than the arterial trunk pressure. So both valves are still closed. As the pressure grows in the atrium, then the atrium will relax here still, but it will have filled up with blood. And the ventricles are relaxed. The ventricular pressure will be less than the atrial pressure, or the atrial pressure would be greater than the ventricular pressure, and it would also be, the ventricular pressure would also be less than the arterial trunk pressure. So the semilunar valve is closed. So the AV valve opens, and the semilunar valve is closed, right? And here we go back again to atrial systole, where the atria contracts. So learn this chart, learn what is open and what is closed. Again, depending on what your lecture professor told you. Know the pressures and which one is vice versa. Which valves are open or closed. And then we will get into some other things as well. So this is just an overview of what is occurring, what pressure is greater. I think the chart's a little easier to understand, but again, go over it and review that as much as you can. This is something that will be extremely important. Your stroke volume, extremely important. Your end systolic volume, extremely important. Let's see. I think we get a little bit further into that as we get into cardiac output. Yeah. So no cardiac output. The amount of blood pumped by a single ventricle in 1 minute. Right? So a measure of the effectiveness of our cardiovascular system. No heart rate, which we all kind of know. Stroke volume, again. Volume is just as important as cardiac output. Volume of blood ejected during 1 beat. So in order for you to get your cardiac output, you would have to know the heart rate plus the stroke volume equals your cardiac output, right? So if your heart rate is 70 beats, and yeah, so here, we don't even have to do it. So at rest, heart rate is 75 beats, and your stroke volume is 70 milliliters per beat. 75 by 70, you'll get 5.25 liters per minute, or 5,250 milliliters per minute, right? You don't have to do the math, but just know its relationship, right? So know that heart rate and stroke volume make up your cardiac output. Again, total blood volume about 5 liters. And it's the total blood volume pumped through circulation every minute, right? So you're essentially, actually, don't quote me on that. So here, smaller heart, smaller stroke volume. Just, you don't really have to know this. Resting heart rate higher to maintain normal. Larger heart, larger stroke volume. So I guess you could make note of this. Larger heart, larger stroke volume. They might ask you, an athlete with a stronger heart will they have a higher stroke volume compared to someone with a smaller heart, not athletic? And you will say yes, the athlete has higher stroke volume, right? Cardiac reserve is another important term. So again, study these. That's kind of on you guys to study and look into. Just at least know every term, know what it means. They will most likely be on your exam. Chronotropic agents are factors that change your heart rate. Positive chronotropic agents increase heart rate, right? So again, make note of that. If you're increasing heart rate, that's cardioacceleratory. Acceleratory, and that would be your sympathetic nervous system, right? So make note of that. I don't believe you need to know all of this. But again, in nodal cells, calcium is that thing that gets us to depolarize. And then negative chronotropic agents. So if the positive increases heart rate, the negative decreases heart rate. And again, that is our cardio-inhibitory. And hyperpolarization means that it went past the resting memory potential, so we're extra negative, so it's harder for it to reach the threshold, right? So it's harder for you to get those fired action potentials because you're further away from the threshold. Venous return is just blood return to the heart by the veins. And if you saw in the last image, there was, or one of the last images here, we have extra blood in the valves. ESV is end systolic volume, and where's EDV? And diastolic volume. So there will be a certain amount of blood in the heart at these times, depending on the contractibility of our ventricles. So know what that means, know what each one means. And diastolic is after the ventricles have relaxed. Again, preload another term. These will be on your exam, so please study these and read these. These aren't concepts that I can really help with you to understand. It's just more so like you understanding the terms and how it interacts with the heart. Volume of blood returned to heart via great veins, that's venous return. And again, its relation to stroke volume, which was up here. So volume of blood ejected during one beat. So if more blood gets returned to the heart, then you can eject more blood out of the heart, through stroke volume. Okay, so we'll continue. Again, just some more things helping you understand. I'll start that just so you can get a better understanding of venous return. Low blood volume. So if you have less blood, you'll have less venous return, making your stroke volume less, making your cardiac output less, right? So if they ask you what's the relationship if you decrease blood volume and how does that affect stroke volume, or how does that affect cardiac output, it will be, it will decrease the cardiac output because you're decreasing your blood volume, and that decreases your stroke volume, and your heart rate times your stroke volume equals your cardiac output. Right, so I'll write that out. So venous return will count as VR. If your venous return decreases, that means that your stroke volume decreases. And if your stroke volume decreases, that means your cardiac output decreases. And the reason your cardiac output decreases is because your cardiac output is equal to your heart rate times your SV. So your venous return also decreases with high heart rate. So if your heart rate is higher, right? So if your heart rate increases, then you have less venous return because there's always just more blood flowing. So you're firing your heart faster. So the stroke volume will also decrease, but because your heart rate increases, the cardiac output can remain the same, depending, right? Because if your stroke volume does not decrease, and your heart rate does increase, then you will have a greater cardiac output, but with relation to always being the 5 liters, right? Again, Frank Starling law will help you understand the relationship of venous return on stroke volume. So read that. That will be important to the exam. Afterload is also an important term to note. Inotropic agents, they alter contractility. So how forcefully a chamber of the heart contracts, or how forcefully the heart contracts. And then again, depending on what your professor has told you, you can email me and I can always make another video try and explain it, or we can do a tutoring session. I can explain it then. But I don't believe you need to know this very well. But if you want to, or if your professor has told you that this will be on the exam, email me or see me for tutoring, and then I will explain that further. Afterload, like I said, important term to know. You're going to have 20 questions on the heart, 20 questions on the endocrine system, 20 questions on blood vessels. I don't think I'll be able to make a video on blood vessels, so please study that on your own. You need me too much for that one. I think these other two are a bit more complex. Here, heart rate and your stroke volume are explained a little further. And your cardiac output, again, these are the terms you really want to know. And I would say if you're going to know any of these clinical views, it would be these. Bradycardia is